In computing, the term server traces its origin to mid-20th century queuing theory. Specifically, it relies on Kendall's notation, a mathematical model used to describe how entities wait in a line to receive a service, and how a process efficiently handles them. On a modern network, we call this the client-server model. A server is simply a computerized process that provides resources, data, or computations to calling clients through a continuous request-response loop. Because a server is defined by its mathematical role rather than its physical casing, any general-purpose computer connected to a network can host one. The hardware used to host the very first World Wide Web server was a standard desktop computer at CERN, running a background process. If a basic desktop computer can successfully serve data, the transition to heavily segregated software roles and massive specialized hardware arrays represents a shift toward managing extreme volume and reliability. To understand scale, we have to build a server from the hardware up. We have to examine the rigid requirements of physical fault tolerance, and then deconstruct how web and application software architectures divide the labor. The modern server functions as an orchestration of specialized physical and logical layers, each designed to eliminate specific systemic bottlenecks. Defining a machine as server-class hardware means it is engineered for two exact metrics: absolute uptime and total remote management. Because these machines are accessed over a network, they are built to be headless. They lack monitors, audio interfaces, or graphical user interfaces. Instead, administrators configure them remotely using out-of-band management systems like IPMI. Enterprise servers require redundant components for survival. To prevent crashes, they use error-correcting code memory to fix data corruption on the fly. They also feature dual power supplies and hot-swappable disk arrays, allowing technicians to replace failed components without interrupting the server. Over the last decade, the physical architecture of these racks has evolved heavily to support artificial intelligence and large language models. AI workloads require executing millions of mathematical operations simultaneously. Standard central processing units cannot process this efficiently, forcing a shift toward massive parallel processing GPUs. These chips are bound together into massive clusters using specialized high-speed physical interconnects, allowing multiple GPUs to communicate rapidly enough to train complex neural networks. But this highly redundant hardware provides only a physical foundation. Without an architectural division of software to organize the incoming traffic, raw physical power is useless. If you deploy a single software process to handle all network tasks, you create an immediate bottleneck. The labor must be divided. The first distinct software layer is the web server. Its mandate is strict. It exists to deliver static assets like HTML text and image files to clients over the HTTP protocol. If a server spawned a brand new process for every single image requested by millions of users, the system would lock up. To solve this, the web server utilizes a non-blocking architecture called an event loop. Instead of waiting for slow operations to finish, the event loop registers a request, hands the file retrieval to the operating system, and immediately loops back to accept the next request. Web servers are highly efficient engines for rapid static delivery. However, they lack the architecture to calculate dynamic, interactive business logic. To calculate customized variables, like applying a discount code in a shopping cart or authenticating a login, you need an application server. When user interaction requires dynamic logic, the web server's event loop is insufficient. The application server takes over, handling these complex tasks through multithreading to create simultaneous parallel threads of operation for a single request. These individual threads can use protocols like RMI or RPC to reach out and query external database management systems concurrently, gathering the exact customized data the user asked for. The application server provides the heavy computational lifting, yet it entirely relies on the web server to act as a frontline shield, filtering out the overwhelming volume of static requests so the application server only computes what is necessary. When clicking checkout, the request hits the web server. It instantly delivers static images, then proxies the dynamic request deeper. The application server receives the handoff, applies business logic, queries the database, and renders a new HTML page, passing it back. Finally, the web server completes the cycle by delivering that customized HTTP response back to the client's browser. This instantaneous proxy handoff between static and dynamic engines enables the interactive capabilities required by modern web applications. In the early 2000s, dedicating single physical machines to specific software roles created massive hardware bloat. The average utilization of a physical server sat between 5 to 15%, wasting the majority of its computing power. To solve this inefficiency, engineers deployed specialized software called the hypervisor. It abstracts real hardware, presenting virtual CPU and RAM components to the operating system, allowing a single physical server to be partitioned into multiple virtual machines, each running its own isolated server process. But scaling this hyper-dense, virtualized client-server model across the globe comes with an inescapable physical consequence. Maintaining millions of enterprise servers, especially the GPU clusters required for AI, requires industrial cooling infrastructure, driving a massive environmental footprint. This chart shows the energy demand of these facilities. In 2024, data centers and their associated cooling infrastructure consumed 415 terawatt-hours of electricity. That single metric represents roughly 1.5% of the entire world's electrical energy consumption. The modern server operates as a duality. It is a purely logical abstraction of software roles, event loops, multi-threading, and virtualization that ultimately demands an uncompromising, resource-intensive physical reality to survive.